So, all right, I'm going to stop sharing and I'm going to go ahead and get us started on the introductions, Lindley. So if you want to go ahead and start sharing your slides, I'll get us going.
Sounds good.
All right, so welcome back everybody to the SMU Physics Department Speaker Series for Spring 2021. And we're beginning our April series today. This is the last month of the series and its theme is From Subatomic to Cosmic. And in a moment, I'll introduce today's speaker. Well, I'll introduce Professor Jody Cooley to introduce today's speaker. And our speaker today is Professor Lindley Winslow. But before we get going, I just wanted to make some of the usual reminders. So to our audience on Zoom, to ask a question, just type the word speak in the chat window to indicate you want to speak, and we'll interrupt the talk at the next opportunity, like a slide boundary, or and then we'll get to your question. You're only going to be able to speak when you're called upon by a moderator. We have to unmute you. And that's because the event is being recorded and simultaneously live streamed on YouTube, and we don't want anyone to be embarrassed by a hot mic. So let me go ahead and with those things in mind, hand things over to Professor Cooley to introduce today's speaker.
Thank you, Steve. It's my pleasure to introduce Dr. Lindley Winslow today. She's an associate professor at MIT. She received her BA in physics and astronomy in 2001 and her PhD in physics in 2008, both from the University of California at Berkeley. After a postdoctoral fellowship at MIT, she was appointed assistant professor at the University of California, Los Angeles. Dr. Winslow was appointed as an assistant professor at MIT in 2015. She's won several awards, including the L'Oreal for Women in Science Fellowship in 2010 and the 2016 Breakthrough Prize as part of the CamLAN collaboration. Dr. Winslow is an experimental nuclear and particle physicist. Her work focuses on the physics of fundamental particles Her work focuses on how fundamental particles shape our universe and the development of specialized experiments, including novel detector technology and algorithms to address these questions. Her current work focuses on searches for neutrinoless double beta decay and axion dark matter. Lindley, thank you for being with us today.
Thank you, Jody, for that great introduction that goes very nicely with my title of my talk, Axion Dark Matter and Neutrinos Double Beta Decay. So that's what my group works on. We work on searches for axion dark matter and neutrinoless double beta decay. And so hopefully you all are seeing the slides advance. So what am I going to tell you about today? I'm going to tell you about my experiment ABRACADABRA. I'm going to tell you about CUORE and the following next generation experiment, CUPID. I hope to get to telling you about CamLAN and NuDot, but depending on what you're all interested in, we may or may not get there. So what are you going to hear about as far as technology? Because that's really what you're following here. And you're going to hear about cryogenic sensors, bolometers, scintillating bolometers, liquid scintillators, and directional liquid scintillators. The last, of course, if time permits. So let's start with the big picture. So this is one of my favorite pictures from physics and astronomy, the Hubble Ultra Deep Field. And as you stare at it, of course, it's just amazing to look at all the detail of its galaxies. But then if you put on your particle nuclear physicist hat, you start noticing some details. You notice like the arms on the galaxy. And if you kind of stare at it, you start to see like the filaments that are the evidence that, there's stuff out there that we can't see. It's the dark matter that helps that gas fall into the potentials and ultimately what led to those galaxies. And so what we would come to understand is there's a lot of dark matter out there. Then continuing with your particle and nuclear hat, what you realize is it's all matter out there. And so what happened to all the antimatter? And that might be even a more fundamental question. So the big questions that I try to address is what is dark matter and why is there more matter than antimatter? And wearing once again that particle and nuclear physics hat, this is my starting point. This is the standard model of particle physics with the tagline, it's not complete, but it's never wrong. And we're just desperately trying to find something that it does wrong or something new to put into the standard model. So what we know so far is that it has 6 quarks, it has 6 leptons, the most famous of which is probably the electron, and a Higgs boson, the interaction of the field gives mass to everything else. The 3 forces that we know about in particle physics and nuclear physics, the electromagnetic force, the weak force, and the strong force are moderated by the gauge bosons, the gamma, the W, the Z, and the gluon. And what we do know, though, is that it's not complete. One of the hints, though, that we have of new physics is that as you go up in energy, the forces, those three forces I just told you about, the strong, the electromagnetic, and the weak force, they all start unifying. And there's this energy scale, the grand unification scale, or the gut scale, where we think they all become one force, where, you know, once again, there's no strong force, electromagnetic force, and the weak force. It's just all one force. And we really think that at that energy scale, that there should be new physics. And so that's a good place to look. And as I said, we're desperate to find good places to look for that new physics. So if you ask me what unifies axion dark matter and the search for neutrinos double beta decay, it is the search for new physics at the gut scale. And so the axions that interest me on the left are these nano EV axions. They're pretty light axions, which correspond to a gut scale axion. And if you're talking about Majorana neutrinos, you're talking about a seesaw mechanism where you introduce these gut scale neutrinos that then can explain our light neutrinos. And so there's a really nice sort of unification, that was an accident, of these two topics. And they also address other issues we know about in the standard model, namely the strong CP problem and the Majorana versus Dirac nature of the neutrino. And I'll get to those in a minute. So that is the overall, like, big picture reason that I'm looking for axion dark matter and neutrinos double beta decay. It's this interest in these big questions of the dark matter and the matter-antimatter asymmetry, but also sort of more generally the search for new physics at the gut scale. So let's go ahead and start with axions. So axions are different than the dark matter you might be used to thinking about. And so this is my cartoon picture. On the left, you have your sort of billiard ball dark matter, the most famous candidate, which is the WIMP, which I know we have people actively searching for at SMU. And the picture you have in your head is this sort of sea of billiard balls that you're sort of running into. That's your dark matter. Axion dark matter on the right is very light. So the picture you should have in your head is these little tiny balls bouncing around, or actually probably more appropriately, they're so light that you can't think of them as particles anymore, that you need to start thinking of a field of waves. And so this is probably the picture you should have in your head of the difference in the dark matter candidates. So to put some numbers to that, let's talk about the de Broglie wavelength of your dark matter, or the occupancy number of your dark matter. And so if you're talking about a nano EV axion, the de Broglie wavelength is 10,000 kilometers, and with an occupancy number of 10 to the 44. So that's very much a wave-like description of something that's, you know, existing over great fractions of the Earth. The WIMP, on the other hand, has a de Broglie wavelength of 10 to the minus 16 kilometers. So you're really talking about a particle, and the corresponding occupancy number is 10 to the minus 36. So you're really in that sort of sea of dark matter. These are individual particles bouncing around. So once again, axions, you're thinking of a wave or a field, and WIMPs, you're thinking about these really sort of billiard ball models. So then why axions? Why are axions a good candidate for dark matter? And I hinted at this earlier, is that it's because they come out of a solution to a problem in the standard model that we already know about. And it has to do with CP violations. So CP, charge parity, describes a mirror-like symmetry, and a violation of CP leads to particles and antiparticles behaving differently. And if that sort of, you know, spikes a chord in your ears, you know, this is a key ingredient to making a matter-antimatter asymmetry in the early universe. We desperately want to observe more of it for that reason, but we don't see it in the strong interaction. And so there is sort of a general feeling that if something is possible, if there is a Lagrangian term you can add to your standard model of particle physics, that you need to have a good reason for it to not be there. And so this is, on the right, the Lagrangian that you would add to the standard model for a CP violation in the strong interaction. And so that's something that's perfectly fine. It should be in the standard model. This term gives rise to an electric dipole moment of the neutron. And so what you'll notice is that this term has a constant out front, theta. The dipole moment of the neutron is 3 times 10 to the minus 16 times this theta. And so that 10 to the minus 16 number is kind of what you want to remember. A quick side trip, neutron EDM, you're probably familiar with the classical electric dipole moment that you calculate sometime in your early part of E&M. Quite literally, you can sort of think about the neutron similarly, that you have these up and down quarks, and their charge distribution can give rise to an electric dipole moment. If you calculate this just kind of on the back of the envelope, you get something like 4 times 10 to the minus 14. The problem is that we've been measuring this for a very long time, and we just don't observe an electric dipole moment of the neutron. Currently, the bounds are somewhere at 10 to the minus 26, which corresponds to theta bar, this constant out front of the CP violation term, of 10 to the minus 10. And so if you are a particle physicist, 10 to the minus 10 might as well be 0. So we're not seeing CP violation in the strong interaction. So you need an answer for why not. And so the answer comes in the PQ symmetry. So it was proposed by Peccei and Quinn to add this extra field, the axion field. And what you end up with is this term that you see in the left, where the axion field comes in and gives you a constant out front where you're actively, dynamically sending this term to 0. What's neat about the addition of this field is that you end up with a particle, the axion, which is a good dark matter candidate. And so that's why we are really interested in axions, is that it's solving both of these problems. So in general, there are 2 different models of axions that you can look for that would solve the CP problem. They are the KSVZ axion, which introduces some heavy quarks, and a PQ, a Peccei-Quinn scalar. You don't need to know the details of these. It's just kind of good for completeness. The other one is the DFSZ. It is a slightly harder to reach field, reach area parameter space, and it introduces additional Higgs fields, including this PQ scalar, which is the axion. So in general, the KSVZ and DFSZ, these are the QCD axions. They solve the strong CP problem, and these are the models you can go look for that would be both dark matter and solve the strong CP problem. These axion-like particles, they turn out they're made in lots of higher order theories like string theory. They just kind of pop out, and it's actually hard not to make them. And so these are called axion-like particles, or ALPS. When I'm talking, I get lazy because it gets tiring to say QCD axion and ALPS all the time. And so when we're talking about axions, we're usually talking about the combination of ALPS and the QCD axion. And we'd be really excited to see any of these. So what is the axion mass if we're off looking for this new particle? And the answer is we really don't know. There are 2 scenarios where this whole, the Peccei-Quinn mechanism can happen. It can happen before inflation, in which case inflation basically stirs the whole kettle of the early universe, the whole pot, and the mass of the axion can be pretty much anywhere in parameter space from 10 to the minus 2 eV down to the 10 to the minus 22. In a scenario where the Peccei-Quinn symmetry is broken after inflation, then the universe has a lot more to say, and we're something above a micro EV. There's limits coming from stellar cooling, but really we have quite a bit of parameter space to look for the axion in. So yeah, 10 orders of magnitude to search over. So then your question, since I'm your experimentalist for today, is how do you actually detect them? So once again, we're back to the Lagrangian, but don't get worried. It has 4 possible terms when you add this axion field to the standard model that you can use to look for axions. The first one is a coupling to photons, GA, gamma, gamma, F mu nu, F mu nu. That F mu nu is the F mu nu you're used to. And then the others are coupling to various aspects of the nucleon. The next 3 terms, they require more atomic physics techniques. And you also have the issue that you have to include the nuclear physics. And as a card-carrying nuclear physicist, I'm allowed to say that it makes everything a little harder to interpret as soon as you have to do those calculations. And so as far as sort of a very clean measurement, that's why people have really gravitated to this coupling to photons to look for axions. But I will mention that there's a lot of exciting new work being done in how to access these other couplings. So I'm going to go ahead and choose the coupling to photons, which means we're modifying Maxwell's equations. So this should just make everyone on the call happy because we all know Maxwell's equations. And these are the axion modified source field Maxwell's equations. We neglect the terms corresponding to the gradient in the axion field. The axion, the coupling's already weak. We don't have to worry about that. And so what we're left with is a modification of Ampere's law. And so what happens is we have a large parameter space to search over, and we end up with three basic regions of this modified Ampere's law. We have a region where the Compton wavelength of your axion corresponding to its mass is about the same size as your experiment. And in this regime, you're talking about cavity experiments that you're really building to tune to that axion mass. And these experiments look like really hard Jackson problems. The next region you have is the region where the wavelength of your axion is much, much larger than your experiment. And here you have effective currents. And so this is a really nice regime, the so-called quasi-static regime, because you're dealing with real currents. And then this becomes an intro E&M problem, a lot of right-hand rule. And then the last regime to think about is this regime where the wavelength of your axion is much, much smaller than your experiment. And this is where you can actually produce real radiation. And once again, you're back to a very hard Jackson E&M problem. So where I'm actually going to end up is this quasi-static regime, this regime where the wavelength of your axion is much, much larger than your experiment. And this corresponds to the low mass regime. So these are the masses of your axion below about a micro eV. And so I'm indicating here that regime in the red box. It also happens to correspond to a nano eV scale axion. So why is that nano eV scale axion really interesting? Well, that is the axion that corresponds to new physics at the gut scale. And so, as I said, that's something that really interests me. So I'm particularly interested in this low mass nano eV region because of the connection to the gut scale. So this is the experiment that you build to go after your nano EV, these long wavelength axions. And so this is a toroidal magnet. This is the experiment that was written down by my colleagues, Yoni Khan, Ben Softy, and Jesse Thaler. And this is your floating toroid in space. And so what you have is you have a toroidal magnet, the B field's running around that donut. And so the axion will couple to that B field. And so you end up with an effective current going in the same direction as your B field. Now, this current will be oscillating with the mass of the axion, with the frequency corresponding to the mass of the axion. So you have an oscillating current. This oscillating current will generate a real B field. And so you can quite literally do your right-hand rule, thumb in the direction of the current, fingers swipe up through the center of the magnet. So you induce a real magnetic field up through the center of this toroidal magnet, where classically there should be no magnetic field. And as a low background physicist, a rare event search physicist, this is beautiful. I know how to do low background experiments. And so it's a very elegant way to search for axions, because to first order, any signal you see there should actually be an axion signal. To give you a little better idea of what this signal looks like, so once again, picture your wave, dark matter, the axion field A of t equals sine of ma t, so ma once again is your frequency. So if you're looking for your axion, you're going to take your signal coming through that pickup loop. That's the signal that's induced by that oscillating magnetic field through the center. You're going to Fourier transform that signal because you're looking for a frequency. And you're going to make a plot like you see on the right there. So you have frequency along the x-axis and power through your squid through that pickup loop on the y-axis. And you'll have some noise because electronics are never perfect. And the axion signal should be a very, very narrow signal at one frequency that rises up over top of that noise. The natural width of this is about 1 part in a million, that delta F. But it's not a perfect delta function. It has a width to it due to the velocity distribution of the axions in the halo. So in fact, it actually has a very well-known shape that you see here on the right, with a tail off to higher frequencies. So we can actually use that shape in our analysis, and in fact, we do. So, does this experiment work? Because what you saw there was your your toroidal magnet floating in space. And so this is the fun part. This is the experimentalist going to work. So we needed to build a magnet. I needed my toroid magnet. And so this is ABRACADABRA. And what we did is we started with some Delrin, we glued them together to make the frame. And then the wire is wrapped onto that to make your toroidal magnet. It all needs to be supported along with a pickup loop. This is Teflon supporting a pickup loop. And here's the magnet assembly in progress. And so it's all sitting in a superconducting shield. I'm going to point your eye to two pieces here. So this green is the magnet. The wire is running around in these grooves. Here's the pickup loop. And so the flux will be going through there due to the axion field. What we also have is an outer wire, and that is our calibration wire, because we're going to need to inject a fake axion signal to calibrate the experiment, to know that we can induce axions and detect them. And so that's a key part of building a new experiment, is figuring out how you calibrate it. So ABRACADABRA was installed for the first time in the fall of 2017. It didn't work. So we had to do a little bit of surgery. We needed to actually shrink that pickup loop a little bit. And that was completed in January of 2018. Here's the picture of ABRACADABRA installed. It is installed in my dilution refrigerator on campus at MIT. It is sitting here from the 10 mil cave stage, the coldest stage. And here's that superconducting sheath. Superconducting shield. And our squid, the squid current sensors are sitting up here at 700 millikelvin. This is for the first run of ABRACADABRA.
Oh, Lindley, we have
there's one. What?
A question for you. Yeah, yeah. Let me get Tom unmuted here. Go ahead, Tom.
Yeah, I missed something really fundamental here.
No problem.
In your technique, if the flux of axions is presumably isotropic or nearly isotropic, why do you get a net B field through the toroid?
So the axion field is sort of permutating through all space. And so then in the quasi-static limit, what you'll end up with is that field coupling to the B field, and it makes an effective current. And so you need we can go back to Maxwell's equations. And so you're picking up this term here. So dA dt, that oscillating axion field, coupling, and this is a standard, this would be a new parameter, the standard model, GA gamma gamma, to the B field in that region. Does that answer your question? You're quite literally modifying Maxwell's equations here.
Yeah, but I'm still lost. You've picked out a specific direction, right?
No direction. It's just all through space. So yes, any magnetic field that you have will be having some coupling to the axion. We just haven't measured it before. Okay,
I guess my picture was wrong. I was picturing that you had some net flux of B field in a particular direction, and then I couldn't figure out what set the particular direction.
Yeah, no, this is, you can think of it as the axion field, like it's something you might be more comfortable with. It's like an electric field. And so you're having this E and B interplay, just like the other term, dE dt indicating B, dA dt x, just like that oscillating electric field.
So okay, let me think about it more. I had this image of a flux coil, and the axions would somehow produce some net flux in a particular direction. So you get some sort of magnetic dipole moment, but I guess that isn't the case, because if you got some
in this regime. Yeah.
Okay.
Yeah.
All right, let me go away and
you can get more. No, I think it's the fact that it's too simple. This is quite literally modifying Ampere's law. This is like the last lecture you can give in freshman or sophomore E&M.
And Lindley, we have another question here from Rob Calkins. Rob, you should be able to go ahead.
Oh, thanks. Yeah, would you expect oscillations just from the oscillation from the rotation of the Earth and local galactic movement and just
yes. Yeah, I was brushing over axion cosmology because it's complex. The axions are produced athermally in the early universe, and they're produced, I think of it as an excited state. That's probably not the right way. And so then they're sort of rolling down a potential. And so they're in a simple harmonic oscillator potential. And so just in the early universe, they're created in this sort of oscillating field geometry. And so that's something that's a little unattractive about axion cosmology, is that there is an initial parameter, and you don't have that from, say, WIMP cosmology. But it is just true that when that PQ symmetry breaks, you end up in a potential, and they're just going to oscillate in that potential from that day forward. Does that make sense?
Let me, there you go, Rob. You should be able to unmute again. Yeah, try.
Maybe that sort of answered a different question. But I was just thinking in terms of just, with the WIMP wind, you have preferred directions, a directionality, and you get these.
Right.
But this is different.
Yes, and so, yeah, their oscillation is quite literally intrinsic to them. There is clustering of axions, just like you have in the WIMP scenario. And so you would expect a day-night, an annual modulation, a daily modulation, and you would expect structure if you happen to be passing through a stream. And so I showed you this picture, which is the sort of standard halo model, sort of the isotropic cloud. And in fact, if you passing through a stream, like the Earth very well may be, you'll end up with an extra little peak here. And so you can, you'll be able to do, if you detect the axion, you'll be able to detect things like halo substructure. Yoni Khan and the theorists are talking about a fancy word for it, and I'm forgetting what they're calling it. Halo archaeology, something like that. It's a great term, but we just have to discover axions first. That's it. But you were right to think about that. But the oscillating, that's the primary signal, is just intrinsic to the axions, but there is other structure that what you are more used to thinking about for WIMPs. And that all should be there.
Okay,
cool.
I think we can keep going.
Other questions? Okay. But thank you all. Those are topics that I love to discuss, but I just don't put in this talk. So then the bigger question, does it work? And we were just getting to that. Yeah, it still didn't work here. Here's it installed, hopefully working. For those that are aficionados of SQUID readout, there are two options for reading out Abracadabra. There is a broadband readout where you take that pickup loop in the center of the magnet and directly couple it into the SQUID. What's nice about this is that you see all frequencies all at once, and it's very simple and very fast. And if you are given just an NSF eager grant to buy the magnet, this is the option you do. It doesn't require any engineering. You just plug in that SQUID current sensor. The second option is a resonant readout, where you take that pickup loop and send it to an RLC circuit, and then couple that to your SQUID current sensor. Now, this is wonderful in that you get an enhancement of your signal proportional to the Q value, and getting a Q value on order of 1 million is not unheard of. The issue is that you have to build that RLC circuit. And at these frequencies, that is not a trivial capacitor, and it all has to be cooled to millikelvin temperatures. And so that is not a trivial endeavor. And so the answer is there requires a lot more engineering to go into the resonant readout. This is something we're working on. And I point you to my colleagues, Saptarshi Chaudhuri and Kent Irwin's sort of paper that goes through this in all of the detail. And I mean all of the detail. That paper is about 200 pages long, but it really goes through things very thoroughly. So the answer is, for Abracadabra, let's go with the broadband readout because we want to get it done quicker. So the first results were from October 2018. There's a long technical paper in support of that PRL. I mean, this is the data that came out. As I told you, we're measuring that induced magnetic field oscillating through the center of the pickup loop. That's going to induce a current in the pickup loop that's going to go to your SQUID current sensor. And so what you're going to do is then Fourier transform that signal in the SQUID current sensor and plot a power spectrum like you see here. So once again, on the x-axis, frequency, on the y-axis, the flux through the pickup loop. And there's some features to point out here. At low frequencies, there is this forest of peaks. Those are not axions. This whole experiment, of course, is in a dilution refrigerator. Modern dilution refrigerators are pulse tube cooled. And so you have this mechanical vibration constantly in the system. And so what you're seeing here is the harmonics of that pulse tube cooling. And quite literally, if you take the squid signal and put it through an audio program, you will hear the pulse tubes from the fridge. That's not great, but it's exactly what we were not hoping to see, but kind of expected to see, since this is a proof of concept experiment. At high frequencies, we're seeing the limits of our electromagnetic shielding. We're seeing a lot of stuff coming in from outside, but there's this nice region around 100 kilohertz to a megahertz, where we're really at the noise floor of the squids that we purchased from Magnicon. And that's really exciting because we can do an axion search in there. And so just to give you a reference, up here on the blue is zooming in, and that's what an axion signal with its nice little tail to higher frequencies will look like in this data. So we go ahead, and one of the details of this analysis is you can turn your axions off by turning off your magnet. And so we took magnet on and magnet off data. We vetoed any mass points that were in the magnet off and the magnet on data. And so that's about 87 out of 8 million mass points. And our wonderful lead theory graduate student, Josh Foster, went ahead and did a, real honest to goodness particle physics log likelihood template fit through the whole spectrum, and was able to set the limits that you see here. This plot isn't the most illuminating, so let's look at it relative to the rest of the axion parameter space. So once again, on the x-axis, we have axion mass. On the y-axis, the coupling to photons. As experiments get sensitive and more sensitive, they will go deeper and deeper in GA gamma gamma to a smaller and smaller correction to the electromagnetic force. And so here is ABRACADABRA, the first run from ABRACADABRA. Obviously, we are a long way from these QCD axions, but considering this was the first run of the experiment, not too shabby. And just to give you guys an idea of what the other experiments look like, these green bands are from ADMX. They're a long-running cavity-based search for axions. And so those are the green ones, and they've started to hit the DFSC. This blue band is a solar axion search. And so it uses quite literally LHC magnets mounted on this carriage to point the magnet at the sun. And it's been running for a very long time. And there's people for reference. This is ABRACADABRA. It's about the size of a grapefruit. And so it's really the little experiment that could. And that's my graduate student, Chiara Salemi, doing an upgrade for ABRACADABRA. And so speaking of that ABRACADABRA upgrade, we just finished it and put this result out on the archive. And so what we did is we did some work to improve the coupling of the axion-induced signal to the pickup loop. And so here is the pickup loop from run 1. Chiara simulated the coupling, and we moved to a cylindrical design because that's something that we could engineer ourselves. We also cleaned up the wiring and improved some of the details of the circuitry. And we also moved those squids from 700 millikelvin down to the colder stages. And so we have improved the sensitivity of the experiment by a lot. Unfortunately, that improved sensitivity made us more susceptible to environmental noise. And so this time we are no longer at the squid floor. We are limited by basically the vibration of the magnet in the dilution refrigerator. But either way, we improved the limits with this run 3 by a factor of 4 to 10, depending on where we are in parameter space. And we were able to pass that solar axion experiment in some of the ranges, which was exciting. And so this paper is now on the archive, Salemi, Foster, Ouellette. And we're moving beyond that now. And what do we need to go beyond that? Well, we need a bigger magnet. It'll still all be in a dilution refrigerator. We'll move over to that resonant readout. And this experiment is called DM radio. It's one of the experiments that was selected for this new initiatives in dark matter. And we really see it as a program of dark matter experiments, starting with DM radio 50 liter, which should be coming online next year. We are in the final stages of planning DM radio cubic meter, which should be reviewed by the Department of Energy this summer. And I am dreaming of DM radio gut, the actual nano EV search for axions at the DFSZ, that QCD axion. That's going to require a very big magnet, something on the order of the CMS magnet, instrumented for axion research. But it's really good to have dreams. So I'll leave that here with stay tuned for more exciting results. This is the ABRACADABRA team. So Oulette, Salemi, Foster, the lead graduate students and the lead postdoc that make the result happen, along with some more junior graduate students like Callie Roy-Pappas and Andrew Gavin, and our theory colleagues. And then from DM Radio, the consortium, which is led by Kent Irwin at SLAC. So I will leave the dark matter part of it here and move on to double beta decay if there aren't any more questions about that.
Okay, yeah, if you have questions, just type speak in the chat window. Otherwise, we can save them for the end too.
Cool.
All right, I don't see anything, Lindley, so I think you can go ahead. Yep.
Good. Okay, so that was your quick tour through axions. And now I would like to take you over to neutrinoless double beta decay for the time we have left. And so this is really going after that question of why is there more antimatter in the universe? And the way we go after this is looking for this rare nuclear decay, or this never observed nuclear decay, neutrinoless double beta decay. And so it's going after this Majorana versus Dirac nature of the neutrino. And so just a little reminder of the standard model and what neutrinos do. They're fermions, they're spin 1/2. They come in 3 flavors corresponding to their charged leptons, the electron, muon, and tau. They carry no electric charge, they carry no strong charge, they're only weakly interacting, and they have very small masses. How small is those masses? Well, here's a nice cartoon. You have several orders of magnitude between our neutrinos and even the lightest of the charged leptons and quarks. And so the question is, why are our neutrinos so light? And there's one little detail, because neutrinos never make anything easy on you, which is everything we know about neutrinos comes from these neutrino oscillation experiments, which measure a delta m squared. And so we call what we pictured here the 3 mass states, which don't correspond to the flavor states. We call in the normal hierarchy the electron neutrinos associated with these lighter mass states. And in the inverted hierarchy, we call the electron neutrinos something associated with these heavy mass states. And this is an important detail, because what it means is we have no idea what the absolute mass of the neutrino is. We just know that we have these mass differences. And so this goes to a deeper question about neutrinos. It's not only just the neutrino mass, it's a question of how we put that mass into the standard model. And so the option is that we have Dirac neutrinos and Dirac masses, where we have different neutrino and antineutrino, distinct neutrino and antineutrino states. The other possibility, and is only a possibility because the neutrino carries no charge, is that the neutrino is a Majorana particle. And in this scenario, what we've called the neutrino and the antineutrino are just different helicity states of the same particle, that alignment of the spin relative to the direction of motion. And we don't know the difference, we don't at the moment have any evidence of one way or the other. So Majorana neutrinos are really nice, because there is these models, these so-called seesaw models, that require a Majorana neutrino. And the reason that is that a big Majorana mass term can split the Dirac neutrino mass into 2, the light neutrino that we know and love, and these heavy N neutrinos that would have been created in the early universe. And so this is what the mass looks like after you diagonalize the mass matrix. You have a mass term for the heavy neutrinos that looks like mass terms that we know and love. And then the standard light neutrino, it has a Dirac mass similar to all the other particles, but it gets divided by this heavy big sister's mass, this MR. And so this is a very beautiful mechanism, the seesaw mechanism, that naturally, if you put in a gut scale heavy neutrino, sends the Dirac neutrinos to much, much lighter masses, like we've observed. So the other sort of detail of that is those heavy neutrinos are made in abundance in the early universe, they decay, and they produce this lepton number asymmetry. So how do we find out if neutrinos are Majorana? So the answer is this search for neutrinoless double beta decay. And neutrinoless double beta decay is exactly what it sounds. You have a nucleus, it decays, spitting out 2 electrons, the double, and no neutrinos come out. They're effectively exchanged within the diagram. And so just a reminder, this is beta decay. Neutron turns into a proton, ejecting an electron and an antineutrino. It usually takes place in a neutron. So if you have plain beta decay, Z goes to Z+1, and you have an electron and an antineutrino come out. Double beta decay, this is the standard model process that can happen. 2 electrons come out, 2 neutrinos come out. The change in the number of leptons is 0. Then if you have neutrino-less double beta decay, no antineutrinos come out, you just have these 2 electrons. And something to point out is that you've now violated lepton number. You've created 2 leptons and no anti-leptons. And so you've made more matter than antimatter, and that's exciting too. So that's what I would really like to point out here as you look at this cartoon Feynman diagram, is that if you have double beta decay, you eject 2 leptons and no anti-leptons because those neutrinos are effectively exchanged within the diagram. What you're seeing here is light Majorana neutrino exchange. And so at some level, as a particle physicist, a nuclear physicist, I don't actually care about the particle physics and the nuclear physics that's happening in here. I only care that 2 electrons come out. And as soon as those 2 electrons come out, I can start figuring out what the particle physics and the nuclear physics that's going on in the decay is. But just seeing those 2 electrons and you're like golden. And so then there's some detail of what nuclei can do this process. Well, you're going to look at the table of isotopes. Some nuclei can't decay to their daughter and have to skip over it and decay to effectively their granddaughter nucleus. And you can list off the isotopes. This 2 neutrino process that doesn't violate lepton number, we've known about for a long time. In fact, it was first calculated, the rate, with an early shell model by Maria Goldberg-Mayer in the 30s. And what it looks like, that 2 neutrino, looks a lot like plain beta decay. You have the spectrum and the electron energy is shared by the neutrinos. So even if you sum up that electron energy, you end up with a distribution. Now, if you have double beta decay, neutrino-less double beta decay, no neutrinos are there. So you can't share that energy. And so what you end up seeing is a peak at the end of your 2 neutrino double beta decay spectrum. And so once again, as an experimental physicist, as a low background physicist, this is a beautiful measurement because you know exactly where to look and you just have to make sure you're not being confused by any backgrounds in this small region. The problem is, of course, that this is grossly exaggerated for demonstration purposes and that this is a much smaller signal than that shows. So how do we go about measuring this? So you can actually write down, and we're going to be measuring a half-life, and it has 3 components. It has a phase space factor, which is just the kinematics of those particles leaving the nucleus. And just a note that higher endpoint means faster rate, easier to measure. So we're going to want the isotopes with high Q beta beta. There is a nuclear matrix element. You have nuclear physics going on. This is a difficult calculation, but there's been a lot of motivation to do better at it. And these are now within a factor of few, depending on your particular theoretical models. And then finally, you're exchanging this neutrino, so you have the effective Majorana mass of the neutrino in this half-life. And so that's what you're looking for. A little bit of note on this is here that inverted versus normal hierarchy comes back again. This is a plot that you see all the time in double beta decay talks. This is the lightest neutrino mass eigenstate versus M beta beta. And you end up with 2 regions. You end up with the inverted region, which what we've called the electron neutrino, that neutrino that's not coming out in this case, is associated with a heavier particle. And you're up with an M beta beta up here, a little bit below 0.1 eV. Or you're in this red region corresponding to the normal hierarchy, where what we call the electron neutrino is effectively lighter. What you'll also notice is that these bands both have width. The Majorana neutrino introduces 2 phases, but you only have 1 measurement. So this is a real interference of phases, especially going on here in the normal hierarchy. But that's some real width. And that's a favorite topic of double beta decay physicists. Cool. So we can write down how an experiment's sensitivity will go. And the things to point out here is the isotopic abundance. So the half-life will be related to the isotopic abundance of the nucleus you've chosen, just based on how much you can get together. And you might look and choose the highest endpoint experiment because that will be the fastest isotope. And then you see that calcium-48, though a beautiful isotope, has a natural abundance of 0.2%. And so you're not going to want to build an experiment when you only have 0.2% of your natural material to use. You then might move down to the 34.5% for tellurium, and that would be what CUORE chooses. And I'm going to tell you about that in a minute. And so that goes towards the total mass that you can get together. And so your half-life will scale with the square root of the total mass. And then I'll point you to the bottom of this is that you obviously want a low background rate because you don't want to get confused with other things in that tail. And so you're going to, once again, you're doing a low background experiment and you're going to want very good energy resolution so that you don't get confused with that 2 neutrino that you're always going to have along with your 0 neutrino double beta decay. So when it comes to the end of the day, you end up with actually a choice between experiments that are very, very big or experiments that you can build with very good energy resolution. And that's what we've been doing lately. We've been focusing on experiments actually to address this claim, which is very well refuted at this point. And now we're about at 10 to the 26 years, about to hit the inverted hierarchy. And just to give you an idea of what 10 to the 26 years corresponds to in comparing to some isotopes that you might be more familiar with, if you're talking about like carbon-14 dating, you're talking about 10,000 years. The longest lived natural isotopes, they had half-lives in the order of 10 to the 10 years. The age of the universe, of course, 10 to the 10 years. That 2 neutrino, that very rare process that we've just recently started observing in all these isotopes, is like 10 to the 20 years. And neutrinos double beta decay, we are now trying to go beyond 10 to the 26 years. And so these are some of the slowest processes that we've attempted to measure. The only one that is longer is proton decay, which is at 10 to the 30 years. So this is not easy. We're looking for about 5 decays per year per ton of isotope, or better than 5 decays per year. And so only 5 things can mimic our signal per year. So that's been the challenge, is trying to figure out how to get there. And so we've tried a lot of different ideas, and you'll see once again that you have this choice between things that are big and things that are cold and have better energy resolution. And really, we've tried them all. So what did I choose to do? Well, I actually work on both of them, because I think it really depends on whether we're talking about going to that red region, that normal hierarchy, where we're going to need a lot of mass, or we're talking about a precision experiment that we need to do now. And so for now, I'm very interested in these bolometers, these associated with the CUORE experiment, but I'm also working on these large-scale liquid simulator experiments as definitely a path forward towards a normal hierarchy. So first, let me tell you about CUORE and some new results from that. Well, CUORE is super cool, and if I was in like a real lecture hall, I would hope that I got a few groans from that, because of course this is the bolometer experiment. And so bolometers are detectors that you are actually measuring the heat rise in a crystal due to this rare nuclear decay. And CUORE, for those that are on CDMS and super CDMS, of course, is tellurium crystals instead of the bolometers used in super CDMS. And so what we're using is a fancy thermometer, these NTD-based germanium thermistors, to measure this very slow pulse of heat rise due to a decay in the crystal. CUORE is 19 towers, 988 of these crystals, arranged in the dilution refrigerator. And this is, as far as I know, still the world's largest dilution refrigerator. And there is a paper declaring it the coldest cubic meter in the known universe. The caveat being, if there's an alien race out doing double beta decay research, then I would be equally happy to discover said alien race and lose the title of the coldest cubic meter in the known universe. And for reference, there is Lucia Economica commissioning this fridge. So as of this week, the last time I grabbed this plot, we have over a ton year of exposure accumulated in CUORE, and we are actually frantically trying to get that paper completed. What I'm telling you about is last year's PRL of 370 kilogram years of exposure. For reference for CUORE is we're looking for this double beta decay event. Those 2 electrons from the decay can't escape an individual crystal. And so anything that's happening in multiple crystals will get ruled out. We also are looking for very nice pulses. And so the first pass gets rid of those multiple crystal events and any nasty looking pulses. And we're left with a spectrum that looks like this. And what you see here is the beautiful energy resolution that you get from CUORE, around 5 keV. At the endpoint. And so we zoom in right at the Q beta beta region, and the 2 neutrino with this sort of energy resolution is way off to the left here. And we don't see any double beta decay. I'd probably be much more excited if we did. And so we're able to set now the world's leading limit on tellurium, which is 3 times 10 to the 25 years, heading off to the final sensitivity of CUORE at 1 times 10 to the 26 years. And so once again, this is that lobster plot. The lightest neutrino mass eigenstate versus M beta beta. We are currently here and pushing down to here with the ultimate data set from CUORE. We would like to do better than that. So what's next? Well, it's called CUPID, the CUORE upgrade with particle identification. And so we're moving from these CUORE crystals, the tellurium dioxide crystals, to a scintillating crystal, lithium molybdate, where in addition to the heat signature coming from the crystal, we will use a secondary germanium wafer as another bolometer to detect the light from this crystal. And using this technique versus heat versus light, you can do an exquisite separation of the beta and gamma events, the beta events that we're interested in, and the alpha events, which are our primary background in this sort of 3 MeV region where double beta decay is interesting. And so we've been actively working on this. In fact, that's up for review at the DOE this summer. I'm particularly interested in these LMO crystals and have been having a lot of fun growing crystals in the last few years. And a 20 crystal demonstrator is running simultaneously with Edelweiss in the Modène underground lab. And so at that point, I've come up at 5:50, and so I was going to ask if there was any questions on CUORE, or I could go on and tell you a little bit about what's up with CamLens-N.
Yeah, if you have questions, just type speak in the chat window. We'll get you unmuted. People are saving. Oh, there we go. Pavel, yeah, let's get you unmuted. Okay, Pavel, go ahead.
Yeah, just if you go to this plot with the two hierarchies, how soon do we expect to, let's say, exclude the inverted hierarchy? Is it something within the next 2 years, or this is very, very difficult?
So the inverted hierarchy is what the next generation of experiments, that's the goal of the next generation of experiments. And so the DOE is reviewing this summer, the last, the 3 experiments that are standing, CUPID, Legend 1 ton, and EXO. And there'll be a decision by the end of the year. And then it's roughly 3 years construction. And so we're hoping that CUPID emerges from that process as the experiment in the sort of NSAC language of the a large US investment, not the US-led experiment. The others are competing for that US-led title.
Thank you.
And so then I think you'll start hearing about that around 2025.
Very good, thank you.
If the money comes.
Okay.
Okay, I don't see any other questions, so why don't you proceed, Lindley?
Okay. So on the other side of things are the liquid scintillator experiments. And so this is CamLens-N. CamLen was a reactor neutrino experiment that used this 1 kiloton of liquid scintillator to look for anti-neutrinos from reactors. What's happened now is that we have deployed a mini balloon at the center, and xenon doped liquid scintillator is deployed within this mini balloon. Right now, CamLens-N 800 is running, and that has 742 kilograms of 90% enriched xenon in the center there. And of course, liquid scintillators, you're looking at this vibration of the molecules that produces light that is then read out by these 2000 photomultiplier tubes out here on the sphere. And so this is the data from CamLens-N 400, which was the last data set. This is the result from 2016. And so the beauty of the CamLens-N detector is that you have position resolution, where in CUORE we have crystal versus multiple crystal. With CamLen, you actually reproduce the X, Y, and Z of the events in the detector. And so what you're seeing here is the mini balloon, and dust and other things piles up on the edge of the mini balloon. And so you see this high background area on the mini balloon, and you can do a multi parameter fit of position and energy. So we have 40 volumes and position energy to extract actually more information than you would extract from the energy spectrum alone. And that's what we do in the CamLens-N detector. So though you know, you would lose a lot of volume if you just to cut out the dirty regions, we can actually extract all that information in the fit, which is very nice. And so this is the data that is actually still setting the world's best limit on double beta decay at 1 × 10⁻26 years. And so since then, we've been doing this upgrade to CamLens-N 800. And so this required a larger balloon. And so here are your necessary pictures of people in bunny suits, washing film and welding it into place. And I had a bunch of wonderful undergraduates taking part. And here's one in a boat fixing the outer detector. More undergraduates. And a graduate student. And this is CamLens-N 800. And so what you're seeing here on the left is once again that CamLens-N 400 data, that very dirty mini balloon. Here is the labor of all those bunny suits. And you see here, except for a hot spot down at the bottom, a very beautifully clean mini balloon. And I'd like to point out that in this clean region, the double beta decay of xenon 136 is dominating it. And so that is the slowest process ever observed, and it's actually dominating our background in the center part of that detector. And so we have a preliminary result from this, but what's interesting is we're beginning to see some spallation products on xenon for the first time. And so we are actively working on analysis to eliminate said backgrounds. And spallation is when a muon goes through the detector, produces a neutron shower that then breaks up the nuclei. And so this is, for better or worse, the first observation of xenon spallation. And I'll point out the work of my graduate students to build a Bayesian version of this fit that then nicely couples to machine learning algorithms. Because of course, what you're doing is you're taking a picture in time in this detector of these events. And there's a lot of information encoded both in the time profile of the scintillation and in a little bit of shrink off light at the beginning of the detector. So I'm going to stop here for today. And thank you all for talking to me. And if anyone would like to talk to me at another time, I can tell you all about follow-ups and that normal hierarchy experiment that will get you to the normal hierarchy. It involves high-speed photodetectors and quantum dot-loaded liquid simulator.
Well, you're really fishing there, Lindley. Yeah. All right. Well, no, let's thank Lindley for this.
But next time.
Yeah, so we're happy to have you back. We're going to get you to Dallas at some point. So, all right, we'll give you a little applause here. And
thank you, everybody.
Yeah, we'll open it up to questions. So, yeah, thanks, Tom, for actually typing the clap, clap, clap in there. Tom, you had a question. Let's get you unmuted. Go ahead.
Yeah, for axions, my thesis advisor was a man obsessed with hunting for magnetic monopoles, so much so that I think he turned off he turned off almost every graduate student went through his regime. When do you give up hunting for axions? I know that's a hard question to answer. What limit is there any limit that would be particularly interesting? I mean, assuming you don't find them.
Yeah, so what's interesting is we definitely have bounds coming from the low end on just what wavelength of axions could be the dark matter. And so when you look at this next sort of suite of experiments, we're kind of covering the phase space of the QCD axion that would be interesting for both dark matter and the strong CP problem. And so I think, you know, in the DM radio family, we do the job at low frequencies, at low masses, and the cavity experiments, I think, will clean things up. And then there's this fun experiment called Mad Max, if you really love Jackson E&M, which is really doing that radiation regime, those high mass axions. And then you have a hard limit on the axions at the higher masses from their ability to be dark matter. And so it's kind of a nice picture. So I would say your answer is about 30 years or however much longer I have in physics.
It's a wonderfully self-serving answer, Lindley.
Oh, it is. It's so self-serving.
Tom, did you have a follow-up to that?
No, I guess I just, you know, it's the age-old problem. When do you give up and say there are no axions, and the CP strong problem really is a problem that, you know, we need to address, and it's, you know, it's another failure of the standard model.
So I guess, you know, I have talked to my theory colleagues of like how much of a problem is the strong CP problem. And like everything in the standard model, it just like, if it doesn't go away with axions, then it's just like another black eye on the standard model. It's just ugly. And maybe it's just what nature chose, but it's just not pretty. So it's not, it doesn't necessarily have to be there, but it's really ugly where it is now. So, so it's a good place to poke. Similar to the fact that the neutrino masses might just be light. They could be light Dirac neutrinos, but it is kind of weird that they're so much lighter.
Right.
And so once again, good place to poke. Yeah.
Okay, and next up we have a question from Pavel. So go ahead, Pavel. let me try again. There we go. I think I got you unmuted this time.
All right. Well, no, I just wanted to follow up on Tom's remark. Indeed, theorists feel very uncomfortable about fine-tuning in the standard model. I think the strong CP violation is a glaring example of something that is kind of missing. And so the axions are such a beautiful explanation that it's also natural explanation. I would say it's more beautiful than supersymmetry. And so therefore, I would not stop looking for them because it is such an important feature of the standard model or extensions of the standard model.
I need Pavel to review my proposals from now on.
Thank you.
Then let that be a lesson to the audience about the importance of giving seminars and colloquia. Yes. All right, next up we have a comment or question from Durdana. Okay, Durdana, you should be able to unmute now.
Hello. I have a question about the last part of your talk about xenon balloon. So do you actually face the same kind of challenge in terms of having to purify your sample? And are you using the same methods as xenon wonton, or you have your own sort of method? And the second question I have is, did you ever review the possibility of actually using solid xenon detectors? Because the proof of concept was done at Fermilab.
Mm-hmm. Yes, so people always point out that xenon is the one isotope that you could do bolometers, TPCs, gaseous TPCs, and liquid xenon with, and so it's beautiful in that respect. The solid xenon bolometers are they're just hard because you have to actually kind of grow them in place, and so that makes bolometers already a tricky technology even more tricky. Camland on the other side of this is quite literally xenon will dissolve in anything, just dump it in. The xenon is purified with very similar techniques before it's dissolved as for xenon wonton. And then the balloon, of course, is like washed and has all sorts of things, anti-static modes and detailed humidity requirements so that it doesn't get too dry and get radon on it. But yes, it's a lot of the same stuff that you will have heard from other experiments.
And let me see, Durdana, did you want to follow up? You can unmute if you wanted to follow up on that.
Sure. No, I just wanted to say that basically self-shielding of xenon in its solid state sort of was elevating a lot of problems, and since the ionization and scintillation readout is possible, I was just curious why that wasn't sort of like an option to try, but I understand your point. Thank you.
Mm-hmm.
Okay, and next up we have Tim. So Tim, you should be able to unmute. Go ahead.
Yes, thanks, Steve. Can you hear me?
Yes, you're all set. Tim.
Yep.
Okay, great. Yeah, no, thanks for this really nice talk. I thought I'd ask, I realize you concentrated on axion photon interactions, but you mentioned briefly the coupling to nucleons as well. And I was wondering, you specifically mentioned the interaction with the axial charge of the nucleon. And I'm wondering, to what extent is knowledge of the axial charge distribution in the nucleon relevant? Is there some sort of form factor that you care about in principle? And to what extent is that maybe a limitation?
Right. And so, yes, so this is where there's been an active interface of sort of, people at the atomic theory interface. They're actually the ones driving a lot of these experiments. And so, yes, that's a worry. But, there's versions of the form factor calculations. And now it's sort of pushing on the details of the experiment of like, how much polarized xenon can you have? Can you actually achieve the NMR sensitivity that you would like for other items, so other couplings? And so this is the Casper Wind and Casper Electric program. And I need to come up with some baseline slides because everyone loves hearing about them. Or I can tell you to invite Alice Shishkov from BU. He gives an excellent talk.
Okay, excellent. Yeah, thank you. That makes sense. I appreciate that answer.
And I think we'll take your suggestion there for our next season. Excellent, Lindley. It's always nice to see somebody throw their colleague under the bus for a seminar or colloquium. All right.
I also was, yeah.
No, go ahead.
There's also some very nice, there's Mariana Safranova from University of Delaware, who's definitely working right in the parameter space that was being asked about, and a younger person whose name is completely escaping me, but she's going to give a wonderful talk at the workshop before the April meeting on precision measurements.
Okay, well, I'll bug you an email for that, Lindley.
Yeah.
All right, I don't see any more questions in the speaker queue. Last call for questions here at the end. Okay, I don't see anything else. So Lindley, thank you very much. Again, we will strive to get you to Dallas in the normal times again after this pandemic is over, but we really appreciate you spending the time and sharing your knowledge with us. So thank you very much.
Thank you all for having me. It was great. Have a good day, everyone.
Yeah, you too. Have a good evening. Bye-bye.